Greetings and welcome to Making Stuff with Chris DeHut. In today's video we're going to discuss this little guy. This is the HC SR04 sonar. It's a distance measuring sonar. They work very cool. They make a few clicking sounds that you can't hear, and then it'll measure how long the echo takes to return to it. Programming them isn't too bad. Wiring is a little more complicated than some simple sensors, but nonetheless they're very fun to play with and great for certain projects. What we're going to cover today will be what the HC SR04 sensor is, what it is used for, how it works, some applications for it, and a few warnings about drawbacks when using it, and how to wire it up. It's a little complicated, but not too bad. And then we're going to go over an example program that will take measurements continuously in both inch and metric. The HC SR04 is an ultrasonic sonar device. It allows us to transmit a series of ultrasonic sounds and then wait for those sounds to return in the form of an echo. And then we can measure that time between transmit and receive and calculate the distance based on the speed of sound. It's truly that simple. Here you can see the device. This particular unit is the transmitter. This is the receiver. So the sounds would come out of this one, bounce off of something, and then come back to the receiver. Most of these devices have four simple connections. You will have your voltage in, a trigger signal, an echo output, and then a ground. On the back, there's definitely a series of ICs that control the whole gizmo. But in our case, it's from a perspective of programming it and using it, it is truly quite simple. The devices are used to measure distance, so anytime you want to measure distance is when you would use this type of device. They have been found and used very commonly in small robotic applications, so that your little floor crawler or roller device or robot can move along and send out a sound, get the feedback back, and determine how close it is to hitting something. Now, in theory, these work very well, but in practical application, they are problematic at best. That's not to say you shouldn't use them. Frankly, they have many good applications, but you have to be aware of their limitations. If you take this device, and for example here, if I'm measuring from the device to the monitor, which is right above the camera there, this will transmit and receive because I'm shooting this signal at a straight, flat, hard surface, and I'm at a right angle to it. But the more I get angled to that surface, the less accurate it becomes and less reliable. The other thing is if I'm shooting it against a soft surface or a fluffy surface, you won't get as accurate a readings or as good a reliability. So for these to work, you need an object that's big enough to send the sound against and have it echo straight back at it, or reasonably straight. So you have to be at that right angle to whatever surface you're measuring to. The surface has got to be hard enough to reflect the sound so you get a good solid echo back, and it has to be big. It's got to be a large enough surface. For example, if you're trying to detect where this pencil is from the sensor, that may not work at all, and perhaps not very reliably. So don't think of these devices as laser-focused measuring sensors. They're just not that precise. One of the concerns I have about these is the quality or lack thereof. They are very inexpensive. For what you're getting and the complexity of the device, the cost is very low. But sometimes you get a bad one, sometimes you don't. I usually buy them in a package quantity of 5 of them, and that way I'm pretty well assured I'll get at least 4 that'll work out of that package. But aside from all that, they are a lot of fun to play with, and you can build some pretty interesting projects besides just using it to sense distance for robotic applications. You can build a sound-based tape measure, if you will. You can do a lot of fun things with them. Now, before we go into the wiring diagram and into the source code, let's take a look at how it works first, and we'll run the software and show you what's going on. Then we'll back up, go through the wiring diagram, and then into the source code. On the bench here, you can see my test rig. I've got a tape measure set up. Over in this direction, there's a wall, so at some point the signal's got to hit it and come back. And it's pretty much at a right angle to my sensor. I'm going to start the program running, and immediately it'll start giving us measurements. Now, where it's sitting right now, it thinks it's 25 inches away from the wall. Here's 25. So it's probably off by about 1/2 of an inch, because I really don't know where the sensor is relating to. If it's relating to the back where the PCB is, it's actually really, really close. If it's up to the front, it's off by 1/2 of an inch, give or take. But as you can see, it's getting a fairly consistent reading here, and it's fairly stable, floating about 1 inch, about 25 millimeters, give or take. But as we move this back, I'll go almost off camera here, and it's showing that that is 31 inches away. And again, we're pretty close according to where the sensor is. Coming forward, we'll go all the way to the left, just about off camera, and that's showing 16 inches, 16 or 17. So it's got about a 1 inch fluctuation. Now, if I want to measure up to the ceiling in here, at this point, it's saying it's 56 inches to the ceiling, which is about right. And as I come up, it's showing 50 inches. So I've come up about 6 inches off the workbench. That's how fancy and neat this little system works. Looks kind of scary, but I'm sure with a little creativity on your part, you can package it up in a nice 3D printed enclosure and have a little more fun with it that way. Now, aside from just the SR04 sensor and your Raspberry Pi PICO, you're going to need a level shifter. And you can pick these up very economically. They're usually $1, give or take, and you can buy them in quantities, 5, 10, something to that effect. Some of them have 8 conversion points, some are only 4, some are bidirectional, some are unidirectional. The current type that I'm using of this particular variety, you can find these on Amazon. I'll try to provide links in the description below for both this and for the sensors. But nonetheless, you will have to pick this up because the sensor is 5 volt, and we're reading directly its input and outputs without any other filtering or anything to adjust the voltage down. If it's 5 volts, it's going to output 5 volts to the PICO, and that's generally a bad thing because the PICO is a 3.3 volt device. So we'll take a look at this in the fritzing diagram, and it looks scarier than it really is. Of course, up here we've got our sensor, our PICO, and then this is our level shifter. Off the PICO, we're going to provide 5 volts from this pin and bring that out to the positive rail up above. And then we're also going to bring ground up to that rail. And those are going to be brought into the sensor. Here's our black wire going in for the ground, And that really should be a red wire. I'm going to change that real quick so it's a little easier for you guys to understand a couple of months from now. But here's our 5 volts coming in at VCC. So now our level shifter needs to have both voltages and grounds brought in on both sides of it. So this would be the 3.3 volt side of it, and this is the 5 volt side of it. So I need to take 3.3 volts, bring that down to the positive rail, and then feed that into our LV, low voltage side. I've got ground coming off of this pin, brought over on the ground rail, and that's ground coming to the low voltage side. Opposite, our high voltage stuff comes in the same way, except for, of course, it's coming on the high voltage side of the level shifter. Now we've got to go from our inputs and outputs to the device. So the trigger is a pulse that we're sending to it. So in our case, GP15 would be our trigger signal, and that's an output. That's going to go through. We'll connect that to TX number 1, meaning that this is designed to handle the voltage going in this direction, where here it's 3.3, here it gets to 5 volts, and that'll go into the trigger side of the sensor. Once the sensor runs and we want to look for the echo signal, that's going to come out this pin over to here to the receive X side, or X input, or receive input. This is the low voltage side, comes over to an input pin, in our case GP14. Coming back to the breadboard, all of that looks much more messy here with these long wires, but nonetheless it is exactly the same as what you see on the Fritzing diagram, just a lot cleaner. So hopefully you get a good idea on the wiring of it. If you follow the Fritzing diagram, it is truly that simple. Now we'll go ahead and look at the source code, or our program for this, using Thonny. I've added a few comments at the top of the program to tell us what the program does and which sensor it's for. Talks a little bit about how we're measuring. We're going to take a measurement about every 200 milliseconds, and I'll explain the importance of that a little later. And it'll return to us an inch and a metric value if the value or the reading was good. If it was a bad reading, it'll return negative 999, just so that we can easily identify a bad reading. I'm recommending you follow the wiring diagram provided on the YouTube video, which of course links you to the Fritzing diagram. And then it is important to add that voltage divider between trigger and echo and the PICO. We're going to import 2 libraries, machine and the pin component of it, so that we can have access to the hardware pins, and then we're going to import the time library, in this case the microtime library. We're going to create 2 objects that will be used to give us software connection to the hardware pins. So the trigger pin is on GPIO 15, and that pin is an output because we're going to send the trigger signal to the device. Pin 14 will be our echo, and that's an input. When the echo goes high, we're going to see that signal and know that the sound was transmitted to something, echoed back, and we can measure that. We want to set that to pull down. We want that to be assuredly at 0 volts and not floating. Now essentially these 2 lines create our electrical interface between the PICO and the device. Now before we get into the function, let's look at how the program runs down below in the main loop. This would be your typical main loop of a microcontroller program. This line here is actually calling the function to make the measurements, and it'll return to us an inch distance and a metric distance. Now I've got 2 different ways I'm printing it out down below here, and you may want to experiment with that. The first one will print any result coming back good or bad. The second one, if inch distance is greater than 0, meaning it wasn't negative 999 as a flag for a bad measurement, it will print it out. Now, you may see times where your loop isn't constantly printing down here and it gets stuck. It just sort of stops. Well, that's because you're getting a bunch of bad readings. And that's when you would want to turn this line on so that you see those bad readings come in. And we've got this whole loop slowed down so it runs at 200 milliseconds each time through the loop. If we go too fast, then the sensor doesn't have time to process all the information. And that'll make more sense in a moment. Coming back up to the function, here we see a couple of variables that we're setting up right at the beginning of the function. First, we're going to create a variable that'll hold the millimeters per microsecond. And that would be millimeters per microsecond relative to the speed of sound, and inches per microsecond, and so that would be inches per microsecond speed of sound. And then finally another variable saying read quality equals good. Nothing really magical there. Now we're going to start up the sensor, and these are the very important little guys that do a very important part of our work. We want to start with a device in a known state, and low being that. So we set the trigger to low, and that is setting that output pin to low. We're going to wait 20 seconds, and that's just to allow time for the sensor to clear itself. So 20 seconds is the absolute bare minimum that we could do down below here. But even at that, that's not accounting for all the other work that would go on in here. Now this small loop here is going to record a moment in time when the transmitting sound pulses end. And we do that by checking echo.value to see if it's 0. As soon as it's 0, we know we've stopped transmitting the sound. And then in that case, we're going to record that time and start time variable. The next one here is the one that actually does the work for us. And that'll be, we're going to wait until the sound goes high again. And that would be the echo coming back to the receiver. So we're going to wait here, keep echoing, or keep checking echo until the sound comes back, at which point this will go high. And we'll record that period in time into the variable end time. So now we know what time it stops sending the sounds, and we know what time we receive the sound back in the form of an echo. Now our duration, the time from start to end of that journey for that sound pulse, we're calling DUR, duration, is the end time minus the start time. If that duration is greater than 24,000, that's beyond the capability of this sensor to actually measure that, so it's a bad reading. So we're going to call that read quality equals fail, and then we'll break out of this loop. Down here is where we're going to clean up the data and make it useful for us. If the read quality is equal to good, meaning we didn't execute this, the duration was less than 24,000. Again, we'll say duration equals end time minus start time, and then we want to divide that duration by 2. And the reason for dividing that by 2, we only want to measure a one-way trip, not a two-way trip. That would be double the distance, of course. So our inch distance is that duration times the distance per microsecond. And then we're going to round that up to a whole number. Then our m distance, metric distance, is duration times millimeters per second. And round that up to a whole number. And then finally return the inch and the metric distance. And here is our catch-all for the failed reading. And that would be returning I distance and an M distance of -999 because that's how we communicate back to our main loop that we had a bad reading. And that is the purpose of this line right here. So as you can see, this is really nothing more than doing essentially a very simple thing. We make a sound and measure how long it takes to come back to us. Half of that time is the time it takes for the sound to get from here to the destination, the one-way trip. And because we know that time and we know the speed of sound, we can take that time and calculate with the speed of sound, how far away the wall or the object is. Really quite simple. Let's take another look at how this system operates. Hopefully you understand what's going on in the program, and now we'll use it as a tool so that I can demonstrate to you some of the limitations of this type of sensor. I'm going to take one of my little mini keyboards that I use to control one of the cameras here, and I'm going to hold that out like so. That's a nice hard flat surface. So from 18 to 29, we've got roughly 11 inches there, right? So if I go here, that should be about 10 inches, and we're getting 10, 11 as our feedback. Makes sense. Pretty accurate, nice hard surface. It's square to the sensor. Get that back where it needs to be. And we're good to go. Well, if you're using this for robot navigation, there are small objects that could interfere with you. In this case, maybe it's something as small as a little cleaning swab. So I'm going to hold that at our mark, and I'm going to drag that across. And it doesn't even see it. So that could have been a collision that we were expecting that sensor to resolve for us. Now let's go to an ordinary mechanical pencil. We'll go to our mark. I'll come across right in front of our sensor. A little bit of noise out of it, but certainly not a reading that is anywhere close to what we really needed. How about a magic marker? That's a little bigger. Now keep in mind, we're only 10 inches away here. It's not seeing it. We kind of get something in this area, but it's off by an inch or 2 inches. And it's not repeatable at all. Okay, so that pretty well eliminates the ability or the possibility that the sensor can see these three objects. So now I'm going to go to a slightly larger one. This is a little alcohol bottle, 1.25 inches in diameter, so that's about 30 millimeters, give or take. And we'll bring this across the front of the sensor and see if it can see that. There it was. So between this and the size of that bottle, the sensor can see in this short of a distance. And therein is part of the problem with using these types of sensors. They are only capable of seeing larger objects, relatively speaking, of course. They need a hard, flat surface to echo the sound off of to come back and measure it. And that's why soft, fluffy surfaces don't work really well. And then you have to be at a square angle to it so the sound doesn't go ricocheting off the wall or the object going off into the distance and never echoing back. That's not to say these are the worst devices in the world. They just have limitations, and if you understand that when you go into using it, you're not highly disappointed in your design for the project. I've been down this path many times with these sensors, and I've gone through all sorts of different types of sensors. Infrared distance sensors that work with light, laser sensors that work with technically laser light, and then LiDAR systems, etc. And you really have to pick and choose which type of sensor is appropriate for your project. With that, I think that'll wrap up this video. Hopefully you found it informative. I would like to mention that we have the source code in the fritzing diagram on our companion website. I'll provide a link for that down below. I also have links to sources where you can get these sensors, as well as the level shifter board and PICOs and some other accessories as well. Those links will be down below too. Hopefully you've enjoyed this, and if so, I hope that you subscribe and perhaps even give us a like and click that notification bell. There's about 60 of these videos planned for the PICO series at this time, and that could easily expand into more videos going through different types of sensors and devices that we use with the PICO. And that's going to wrap it up. Thanks for watching, and I look forward to seeing you in the next video.